Welcome to a new video in the video series on systems biology, digital twins, and AI. So this is the first video in block 4, where we are going to start to look at hybrid models, combining mechanistic models with machine learning models, or combining these into digital twins and hierarchical models and so on. So this is sort of putting all of the things together. And in this first video, we will give an overview of black box and machine learning methods and models, and look at some of the most common goals and categories that exist in terms of methods and things you want to do with this. So typically, when you use these type of machine learning models, then you need large databases. So you need thousands and thousands of training data. That's not the case for mechanistic models, but for machine learning models, then you need, but you also can make use of this large type of training data. So if you have that, and you have some kind of black box model, some kind of machine learning model, then we will look a little bit at how to train the model and how to formulate different types of models to be able to use the model. So when you use the model, then you have some new data that is similar to the data in the training data set. It has the same structure and the same type of input, so to say, but you want to generate a new output, a new prediction of the next time point, which is similar to what we have sort of done before when we do simulations. But it can also be classification, to say if it belongs to a specific category or class. And it can also be to generate a whole new object. That's typically what you do in the deep fake type of applications. So that's basically what we'll do now, to sort of look at how to use this new class of models that is black box. So the sort of interactions within the model will not really mean anything typically in terms of the processes happening in the system. It might mean something in terms of the relationship between the data itself, but that's slightly different compared to these white or gray box models that we looked at before, which are we make use of the mechanistic understanding of what actually happens in the system. Okay, so let's jump in. So we will look at them in the same order. So first, predictions, predicting the next time point. And here we look at regression models of different types, or a few different types. And then go on to this classification problem. We look at support vector machines, the k-nearest neighbor, and neural networks. And once we have understood the basics of these neural networks, then we can look at some generative neural networks and GANs, which is a particular type of generative AI. Okay, so that's what we are up to. So starting with the predictions. So in a regression model, then you want to predict the next output from the previous data that you have, the previous time points. And if you also have some input, you want to sort of use that input, because what you do to the system would also impact what happens to the system. So you have some kind of previous time points, and those are the regressions time points. So here, this is the simplest. This is just autoregressive. There is no input here, so it's just AR. And here, what we want to do is to predict the time point at time t. And at our disposal here, we have some regression coefficients, which basically tells us how to combine the previous data points, the x of ti here, which is one or more time points back in time. And here the order of the model is how many steps in time back do we go? And C here is a particular type of regression coefficient that is sort of a constant that doesn't depend on the previous time points. But these phi's here, they tell us how to combine the previous time points. And just as before, we have sort of the model. So this is the prediction of the model, these two first terms here. And then in order to generate the actual data point, we assume that we have some kind of process noise as well, or some kind of measurement noise, either of those. And that's this epsilon here. So this is a very, very common type of model, and there are different versions. And the second version that we look at here is when we have an extra input as well. So when we can do things to the system, and that will impact what happens to the system. So then we have the same thing as we had before, the autoregressive part, but we have an added term which has its own regression coefficients, these betas, but we also have the inputs up to that also goes back some time steps back in time, and here you typically also add that you want to know the input at the time point that you want to predict, because what you do now will possibly predict or have an impact on what happens directly. So this type of models, as you see here, they have no description at all of what happens in the system. They just go from previous time points of data to the next time point, and possibly with some input added. But there is no information about what happens inside the system. And this is a whole field is basically dedicated to these type of models, which is the field of system identification. And in system identification, you work with this type of black box models. This is maybe the most famous book in the field by Lennart Jung, who is a professor emeritus here at Linköping University. And they have developed lots and lots of theories for how to analyze these type of models. Okay, so now let's look at the particular type of prediction, which is not the prediction of what the next time point is in terms of sort of a continuous set of data, but the type of prediction that we want to do now is what category, what class does a particular object belong to. So that particular problem, when we have one or two or more classes that it can belong to, that is called a classification. And one of the most famous and long-standing methods is called support vector machines. So typically then what you do is that you identify a classifier, which is either a line or a hyperplane, if you're in higher dimension, or some kind of other sort of surface that discriminates between the two areas where you have one type of one category, one class, and the other class. And when you choose this classifier, then you want that the point that is the nearest to this sort of plane that distinguishes between the two areas, you want that point to be as far away as possible from the plane. And here you might say that, well, maybe it's not even possible to find a plane, and that might be the case. And then you can expand to a higher dimensional space, and then you get various types of nonlinear versions, and that might allow you to perfectly discriminate between the training data. But then, as is often the case, that the more flexible the model structure is, at some point it becomes too flexible, so you get overfitting, and then you might actually get worse at predicting correctly which class a new data point belongs to. So let's look at here. So here we have some two classes that we have the white and the black circles, which might, for instance, in biomedicine correspond to do you have a tumor or do you not have a tumor? Or will you get a stroke or will you not get a stroke? So you belong to sort of one of two categories. And here X1 and X2 are some kind of information about the system. Might be some biomarker that you have for the patients to categorize them. And we have some training data. So, and because we have training data, this is part of what we call the supervised learning. So here we know that all of these dots up here, they belong to the same class, the black class, which might be that they have a tumor. And the white ones here, they don't have a tumor. And then we want to pick this line here. So we are only in 2 dimensions. So here a line is sufficient to be able to distinguish so that if we get a new point, we can simply tell if it's above or below the line. So here we have 3 lines, a green, a blue, and a red. And let's look at them from this sort of criteria. So the green one is obviously not the classifier at all because it cannot distinguish between, it doesn't sort of go between the 2 classes. So that's not good enough. The blue one does separate between the 2 groups, but here you see that the sort of margin of error here is very, very small. So if you would have a new data point here, if it's sort of just off a little bit because we don't have perfect training data, we have a finite number of data points. This is sort of not separating between the two classes in a maximal way because the nearest point to the classifier is sort of very, very close to the classifier. In contrast, the red one, that the nearest point to the red one are these 2 ones here. And you see that this is much further away from the classifier. So that is the maximum margin classifier. That is the one to pick in this particular case. So that's the basic idea of what classification is about. Pick which class something belongs to, and of support vector machines in the linear alternative, where we do this maximum margin classifier. Okay, so another super famous old-fashioned classic in this field of classification is KNN, the K nearest neighbors. So it's very, very intuitive, very simple. So you simply find, you have a new point, and you find the nearest neighbors, the most similar points that you have in your training data. How many points should you have? Well, that's part of the name. That's part of the K. That's what the K stands for. And then you simply look in this neighborhood, what is the most common class that they belong to? And that's the classification. So here we have an example. So the question is this green dot here, what does it belong to? Is it one with a tumor or without a tumor? So say that the red triangles here are the one with the tumor, and the blue squares here are the one without the tumor. So then the question is this an image of a patient with a tumor or not with a tumor? And you see, it's not obvious here. So you sort of need a method to do it. And here, if we choose K equals 3, and we sort of have a sort of non-scaled directions, or this is with the scaling already included in the plotting, then the nearest neighbor is simply the ones that are within the circle. So we do the circle big enough so that we have 3 of the training data inside the circle. And if we have 3 inside the circle, then we see that we say that this is a red triangle. So this is a patient with a tumor. But here you already see the sort of the limitation, and that is that if we would have picked K equals 5, we have a bigger circle, and then we would have said this is not one with a tumor. So here you see that you have this sensitivity to the K, and again, because you have no sort of knowledge about why you make a decision, it's just in some abstract space here. You just get the value and you have to take it or leave it. And that's that's sort of the limitation with many of these methods, is that they just give an output. You just get something out of the black box, but you don't know if you should trust it or what the accuracy of it is, so to say. Yes, so this is the basis of the KNN, the K nearest neighbor. Okay, so now let's go to the nowadays maybe most famous, most hyped alternative, which is neural networks. And there is a wide variety of different neural networks, but they all follow the same basic idea. So the first is to distinguish between the neuronal network, which is describing an actual brain, and the neurons inside the brain. So that's when you want to really describe the biology. But if you want to use it to do a cognitive task, for instance, classification, but you can also use it for other things, then you talk about artificial neural networks, which take some of the properties of a neuronal network, so a brain. So they take the basic idea that you have neurons that are communicating with each other, and that the strength by which they communicate with each other, how tightly are they connected to each other, that can actually change. And that's what happens in the brain when you are learning things. That then you have these dendrites that grow out and that might reach out to new neurons, or might increase the strength of communication between them. So that's sort of the basic idea. So here we have different neurons, and these are the communicating arms between these neurons. And here the inputs, the red circles, and the outputs are known data. And the blue neurons in between here, they don't correspond to data, but they correspond to the idea that you might have neurons that are somehow modifying. So this would be the neuron that sort of gets the input, maybe the visual cortex or something like this. Here you have lots of, so here you only have one hidden layer, but you might have many hidden layers. Typically you have many hidden layers. And then you generate some kind of output. And as you learn, you sort of change the weight here. And each node is calculating by summing together these inputs according to the weights and according to some formula for how to sum these together. And the details of that, of course, depends on the training algorithm that you use, and also the particular neural network that you have. But just to take some examples, so it might, for instance, be here that the inputs here are all of the individual voxels or pixels in an image. So then you have as many voxels as you have in the image, that has many inputs as you have. And then you modify that in different ways. And this modification might start by combining the voxels into simple identifications of small units, like this is a corner of something, or this is a line, or this is some other type of object. That might be the first layer, and then in the second layer you combine it into more and more things. But typically, even though you might have partially some kind of interpretation of that after a couple of layers, you no longer really understand what's happening. So it is a black box interpretation, and there is certainly no understanding of the underlying processes that is in the physiological system. And if you have this input are all the voxels in the image, then if you do a classification, you want to know, is this an image of a patient with a tumor or not with a tumor? And then you would only have one green circle here, which has two values, with and without a tumor. But it might also be many other combinations. It might be that you have some kind, the inputs here might be the regression points, so the previous time points, and you want to predict the next time point. Or it might be that you have some kind of image which is the input, or some kind of description of the image, and then the output might be a new image. And then you have a generative AI that you have here as many voxels as you need to generate an image. And it might also be that these outputs here are what you use to categorize a string, so a sequence of characters that makes up a word or a sentence or a piece of text. So you see here that this is very flexible. You can have inputs that are what we typically simulate with an ODE model, and the output can be the same, or it can be a classification problem, or it can be a generative problem, to generate an image or generate a text string or something like this. And because of this flexibility, and because this is very hyped, we will have the next 2 videos will focus on these type of neural networks. So we'll dive into more detail of some of the more advanced versions. But I want to say a little bit more just in this first video, and that is this particular case of this generative adversarial networks. That's a particular type of generative neural networks, which is quite recent. So the basis behind neural networks was developed in the 50s and the 60s, and learning networks was popularized by Hopfield in the 82, and then in the 90s they started to figure out how to do the backpropagation, which is the training of these many hidden layers, and that's when you started to really have the more power behind it. It's sort of in the last 20 years or something like this that you really have this sort of power of neural networks. And in 2014, Ian Goodfellow figured out that we can use a combination of 2 neural networks, one to generate a new instance of something. So for instance, generate a new image, and the other is used to classify if this belongs to the training data or if it does not belong to the training data. So to basically see, is this a false image or is it a true image? And then you have these compete with each other. The classifier will be better and better and better at detecting if it's a fake, and the generative neural network will be better and better at fooling the classifier. So they are sort of, as one gets better, the other gets better. So they are sort of competing against each other, so that they both get better and better. And this is sort of the basis of deep fake, that at some point you are so good at creating a new image that the most advanced classifier that we can develop for this particular task cannot say if it's fake or not. That's sort of the goal of these GANs. So you have these 2 neural networks. So here we have an example. Here you just saw a student of mine, Richard, take a little walk. And then we used a GAN, or we trained the GAN first, and then we used it to make it look like a person who hasn't walked like this in any of the training data, to make it look like he is walking in the same way. So here you see a person that has had some training data, and we'll get back to the details of what the training data looks like. And then it looked like he took a similar walk as my student Richard did. And that's sort of what you are used to seeing now in terms of this deep fake. But here you also see some of the typical problems. So you see that this foot here is not very realistic. It doesn't really look like a normal foot. This one looks much better. And this again comes to the limitation that these type of neural networks, they have no idea what the foot is. They only predict the voxels using this combination of the inputs. So there is no sort of understanding of what it's actually generating. And therefore it can generate these artifacts that look very strange to the human eye, to our classifier, so to say, but they don't detect that. And that's because they don't understand that they are generating a foot. They might generate 3 arms, for instance, or 2 heads or something like this. And there is nothing preventing it from that, because it's just generating new voxels or new pixels in this image. Okay, so let's look a little bit more into this just to understand one particular GAN, how it works. And then this is, of course, the basis behind sort of all sorts of other deep fake and modified versions of that is also used to for this ChatGPT and so on. So here we have the same type of neural network that we use to make a person look like he's walking, to make it look like a person is dancing. And this is from a talented graduate student at MIT, actually, that did this a couple of years ago. So basically here we have some source subject and a target subject. And basically what you have here is that you have a professional dancer here that is being converted to a pose. So this is a stickman that describes the pose that he's in all the time. And this is used. This is done using a sort of normal classifier. So this is used using a program called OpenPose. And this is not so basically the new algorithm here is to go from a pose to an image. So this is the first author of the paper. She wanted it to look like she's dancing as this professional dancer here. The training data is that she has been standing in many different positions. So she has been standing with her arms out and with her legs in different positions and so on. And for each of those positions, we have generated a pose. And so we have many pairs. So she has created a video of thousands of images where she stands in different positions, and we have a corresponding pose. So the input nodes are these pose positions, so the angles here, and the output is the generated image. And then basically what you do here in order to make it look like she is dancing as the professional dancer is to then calculate the pose of the professional dancer and then use the trained generative AI that takes this stickman here as input and generates a new image of her standing in some kind of position as an output. So this is the generative AI. This is the GAN that is going from the stickman here to her. And by combining it with a movement that we want it to be like, then we can combine this GAN here that goes from a stickman to a pose with the movement of the professional dancer to make it look like she is also moving like a professional dancer. So you see here that there is sort of many different things that you can use this type of machine learning and neural network type of models for. And this is why they have become so popular lately, that you can use them without describing any of the biomechanics or any of the sort of physiological processes that underlie this here. And in the end of this block, we will contrast these to other methods that do use biomechanics or that do use more physical description of objects, so Unreal Engine and MetaHuman and so on. And then you will not get these type of artifacts, but you also have to specifically develop your model to describe sort of the physical processes. Okay, so that was basically it for this introduction video to machine learning and neural networks. In the next two videos, we will look more deeply into some particular classes of neural networks.